Hi, this is Jim Wyrick from EdgeCase, and I'm here to talk to you about source control made easy. Now, this talk was inspired by a conversation I had with a friend of mine, and we were talking about Git and how it has really kind of changed the way we develop software. It has affected the habits that we have, the way we save changes, the way we have the ability to create local branches and just try things out and commit them or not. And it hasn't always been that way. When we first started using Git, we learned a handful of commands that we used, and we treated Git just like it was Subversion, but with just kind of stranger command names. And it was a little confusing because Git uses terminology that we weren't used to. So once we kind of developed an understanding of Git and how it worked, all of a sudden these commands started making sense to us, and we were able to use Git in a much more effective way. The problem is most people look at Git and they learn it by those handful of commands, and they try to treat Git as if it were a regular source control system like Subversion. So we're going to address that problem. We're going to do it by not talking about Git itself. Instead, we're going to take you on a journey. Let's pretend that you work for a programming house that doesn't currently use source control, and your manager has discovered that, hey, source control, I read about that. That seems like a good idea. So he gives you the job of creating a source control system. Now, unfortunately, you don't have any budget to do this, and you're not allowed to use any of the existing open source systems, so you've kind of got to create one from scratch. So your job is to design and build some kind of source control system that your group can use. We're going to call this the Custom Source Control System, or just CSC for short. And we'll start by thinking back to the old days. You see, back in the old days, when we were working on a system, we'd have a working directory of our files. In this case, we have file 1 and file 2. And whenever we wanted to save off this data, we would create a snapshot. Just use a tar command or maybe a zip command or some other type of command that takes all the files in our directory and packages them up in a single file. We'll use tar as an example here. Now, inside this single file is a manifest that lists all the files that are inside this single tar file, and then also has the data for all the individual files. Now, using the manifest, we can track what files are inside that particular tar file. And so for our first cut at the CSC source control system, we're going to create a command called snap that creates a snapshot just like we did in the old days. It'll create a tar file with the manifest and embedded files. And every time we want to create a new snapshot, we just run the command again and it creates a new tar file. And it will keep track of the version numbers for us. So we can have version 1 and version 2 and create another one. There's version 3. And that works very nice and easy. Now, to get back to a previous version, say we're working on version 3 and we want to get back to version 2, we just untar the file. We unarchive the file into our working directory, and that copies all the files in that tar file into our working directory, and we now have exactly what was in the snapshot for version 2. So it's very easy to create snapshots and to check out new snapshots. 2 simple commands, and that's all we need right now. Very easy, very simple. Now, while very simple, there was also a small problem with our approach. It was a little bit wasteful. Let's look at that. Here's our 3 tar files that we've created, snapshot 1, 2, and 3. And we noticed that we created these snapshots. When we created 2, we changed file 1, and when we created 3, we changed file 2. But that means that file 2 has the same contents in snapshot 1 and 2, and likewise file 1 didn't change between files 2 and 3. We got some duplicate data in our archive. Now, that's probably not a big problem with 2 files, but say you had 100 files and only one file changes between each snapshot. That's 99 files of duplicate data, and we would really, really, really like to eliminate that duplication if we can. Now, what we would like to do is something like this, where we just throw out the duplicate data. However, that doesn't work really very well with the tar format, because tar assumes that all the data is in that one file, and you really can't have manifest files referencing copies of files in other tar files. That just isn't going to work. So we're going to take a radical step and do away with the entire tar file format. We're going to put everything in a single archive, and we will let the manifest files track what should be in each snapshot. We can get back to the exact contents of any snapshot by looking at the manifest files and seeing what the list of files are for that snapshot. The manifest entirely defines that. So, let's put these files in a directory of some kind, and we're going to just put them in there. Now the question is, what should we name these files? And right away we see a problem, because file 1 is stored in this directory twice with the same name under two different versions. So we can't really use the original file names in this directory. We need to get creative in how we call our names. Now we could tack versions onto it or do something, but we're going to choose a very simple file naming scheme. We're going to start with the file name AAAA. The next file will be AAAB. The next one will be AAAC, and so forth. That way, all the file names are unique, and they won't conflict, and we can put them all in just a single directory and keep track of them. Remember, the manifest files have the actual file names in them, so we don't need to keep the actual files on the operating system directory here at all. So now our project archive is just a directory with files in it. In fact, we could make that our current directory and do an ls command in there, and we would just see the list of the files right there, and then we could dump them out and look at them and do anything we want to with them. So now our archive, instead of being a list of tar files that we've saved snapshots to, is just a directory with files in it. The files in that archive have arbitrary names, and the names can be anything that we want them to be as long as they're unique. And we track the real file names in the manifest files. So let's look at that. So let's pull up a manifest file. What's it got in it? It just has the name file1 and its stored name. So the file1 is the actual name of the file, and AAAB is the archived file that contains that contents. Likewise, file2 is the real name of the file, and AAAC is the name of the archive file that contains that information. We can look at it, and it's just a text file containing the file names and their IDs. The other manifests are exactly the same, just a list of the file names and the stored file names. And here's the third manifest. So we can keep track of all the files in this one directory full of funny name files. Just by looking at the manifest, we can still reproduce the snapshot that manifest records. Now you might think that this is a little restrictive because I can only have one level of files. That's easily solved by having nested levels of manifest files. So for every directory in your project structure, every directory is going to be turned into a manifest in our archive file, and we'll just have the manifest keep track of not only the data files but also the other sub-manifests, or the subdirectories that are associated with that particular snapshot. Now your boss is quite happy with what you've done so far, but he would like a little extra added to it. It would be really nice if we could keep track of a little bit of metadata along with our snapshots. For example, we need to know who made that snapshot and what time it was made, and maybe some comments describing it. And of course, we want to keep track of the root manifest for that particular snapshot. So we develop a format that looks something like this. We'll keep track of the root manifest by putting its name into a little metadata file here. We'll keep track of who wrote the snapshot, who made the snapshot, and his email address, along with the date and time in a sufficiently difficult to read format that makes it real computer science. We will also keep the comments that were made with the snapshot, so we can describe why the snapshot was made and maybe the changes that went into it, and a little bit of information so that when you're looking at the archive at a later time you can figure out what's going on. We'll take all this information and we're going to put it into a snapshot metadata file. We'll take that metadata file and we're going to put it right into the project archive with the manifests and the regular data files. That means it gets a regular file name, just like this. The AAAJ is the file name in the archive of that particular metadata file. Now, since it's in the archive and it has a file name, that means we can track it as well. And one more useful piece of information that could go into a metadata file is the information of what the previous snapshot was. So we'll track that like this. We'll keep track of the parent snapshot. And that adds links like this into our project archive. Now, if we just know the latest snapshot, we'll track that in something called the head. By knowing the head, we can go back and see the latest snapshot, and we can go back to the previous snapshot and look at that. And we can go back all the way to the beginning of time and see what all the snapshots are. So, keeping track of one piece of information, the latest snapshot metadata file, will link us to all the other files in the entire archive. So let's just kind of review where we've gotten to so far. We started out with a very simple archive format where we just tarred up some files and shoved them in a directory. And we evolved that to a much more sophisticated project archive that keeps track of individual files along with the manifests that describe the files, along with a little bit of metadata that describes an individual snapshot. Now that's great and it works perfectly so far, but we have to ask ourselves, when we started, creating a snapshot was easy. We just ran the tar command and there you had it. What do we have to do now to create a new snapshot? Well, it turns out there's 4 steps involved. Number 1, you have to go through your working directory and compare all the files to what exists in the archive and figure out which files have changed. And for any changed files, we're going to copy that into the archive. The next thing you do is create a manifest file for the root manifest and any manifest that may have changed since the last snapshot. Those get copied into the archive. You then create a new snapshot metadata record, and that goes into the archive, and it will link to your root manifest, and it will also point to the snapshot that was the most recent one right before you made this new snapshot. And then finally, you relink head to point to the snapshot you just made. Now, this is really interesting because if you notice, our archive is entirely additive. We only add files into it. We never change data that is already in that project archive. And that's a good feature because that means we're not going to accidentally destroy history or accidentally rewrite something. By just adding files to it, we make sure that we preserve its integrity, and that's a good thing to have. Well, I have a confession to make. I left off just a little tiny detail when I talked about creating a new snapshot. Remember step 1 where we said copy the changed files into the archive? Well, how exactly do you detect a changed files? A simple-minded approach might be to go through each file in your working directory and compare that to the latest version in the archive. And then if it's different, it's changed and we copy it in. And that's okay for a simple-minded version. But what if you want to be more aggressive about not creating duplicate data in the archive? What if you wanted to be able to reuse perhaps a even earlier version of that file? Like you added a line and decided you didn't like that and you created a new snapshot that went back to the original version. We should be able to have that original version reused between the 2 snapshots that have the same content. And in order to do that, it's not just checking the most recent version, but it's taking every file in your working directory and comparing it to a bunch of files in the archive. And that can be pretty costly. So we really want a better way of detecting duplication. Let's talk about something a little bit different here. We'll get back to detecting changes here in a second. Imagine you have a file and its contents is something like, "Hi, my name is Bob." Just a string. We can run that string, that content of that file, through a function called a SHA-1 hashing function. And the SHA-1 function returns as output a 40-character hexadecimal number. Now, the interesting thing about the SHA-1 archive is that if you change any bit of the original content, say we changed Bob to Joe, and rerun it through the SHA-1 function, you will get a different 40-character result. That means also that if you have two files that have the exact same content, even though they're different files, running them through SHA-1 produces the same hash. So that tells us that identical content produces identical hashes. So, how can we take advantage of this SHA-1 hash? Let's think about the archive format. We're storing files in a directory. The files in that directory have arbitrary names, and arbitrary is okay because we're keeping track of the real names in these manifest files. So arbitrary names, and they have to be unique because we want to individually identify each of these files. Well, it turns out that the SHA-1 hash for a file name is unique, and it's certainly arbitrary. So why don't we, instead of using our funky AAAA names, what if we used the SHA-1 hash value as the file name in our archive? Now, granted, no one wants to type out a 40-character SHA-1 hash value for a file, but that's inside the source control system. The user's never going to see that, supposedly. So it really doesn't matter what we call these files. To keep track of our head, we just keep track of the file name for the latest commit, just like before, except now instead of a 4-character name, it's a 40-character name. This has a couple advantages. Now let's think about detecting duplication. We take a file, we run it through the SHA-1, and we get a 40-character value out of that. We look up that file name in our project archive, and oh, look, we have a match. That tells us that this particular file is already in the archive with exactly the same content that it has in our working directory, so we don't have to do anything. Let's take another file, run that through SHA-1, and oh, look, there is no match in our archive for that particular hash value. That means this file does not exist anywhere in the archive, and we know that we have to copy it in. Makes detecting duplication a simple matter of looking at file names in our existing project archive. Instead of searching through the entire archive looking for duplicates, duplication detection has become trivial just by using hash names for the file names. Now, as it turns out, there's a hidden benefit for using SHA-1 hash values as file names in our archive. If we look at our archive, we record the SHA-1 hash value as the head, the latest commit. And that SHA-1 hash value is formed by summing up all the contents of that snapshot metadata file, that yellow circle that we're pointing at with the head pointer. That content determines the hash value that is its file name. Now, inside that metadata file is a reference to both the root manifest file and the previous snapshot. So their hash values are stored inside the metadata file. And likewise, a manifest file has the hash values of all the files that are directly in it, and if there are any sub-manifests in there, they reference files that are in it. So based upon the initial head, that hash value is kind of like a checksum of the entire project repository. What does this mean? Suppose, just suppose, that somehow a file got corrupted. Maybe you had a disk error or some hacker got into your repository and was trying to goof you up. Doesn't matter. The contents now of this file is different than what it should be. And therefore, when you run the SHA-1 hash function over it, you're going to come up with a hash value that does not match its file name. So a simple detection of corrupted files can be done just by running the hash function on all the files and checking to see if their names match the hash that the content now generates. Corrupted files are very easy to detect. Let's just suppose for a moment that this corrupted file is not caused by a disk error, but rather by a hacker who's trying to hack into your archive and slip some changes in through a back door. Now the hacker's smart. He knows that the file name is not going to match the hash code of the new content, so he just updates the file name. Unfortunately, the manifest file still points to the original file. It doesn't point to his hacked file. So he's got to go in and change the manifest to point to the new one. Well, that changes the hash of the manifest, which means the snapshot meta file no longer points to the right manifest. Well, he fixes the snapshot metadata file, but now the head no longer points to that snapshot. So by keeping a head pointer to the original snapshot, we know that the entire archive is exactly the way it should be at the point that the head file, the head pointer was created. So there's no way to change a file in here without somehow affecting the head pointer. It's guaranteed project integrity that you can detect just by doing a simple scan of all the files to make sure that the links point to where they should and that the name of the file matches the actual hash value of the content of that file. Simple project integrity. Okay, now let's talk a little bit about tracking snapshots. Your boss wants to be able to go into the archive and be able to pull out, say, a production release that might be several snapshots ago. Now, we know that we can get to any snapshot by following the chain of parent links, but we really would like to track the versions by name. How might we do this? Well, here's your project archive with a head pointer pointing to the latest snapshot. Now, remember, your archive really has manifest files in it and has data files in it, but for the moment we're going to ignore those and just look at the snapshot files themselves. A simple way of tagging a particular release in your archive is to go and create a file that has a pointer to the snapshot of interest. And we create a pointer just by recording the hash code for that particular snapshot. Very nice and very easy. We call these things tags. And the important thing to remember about tags is that they always point to the same snapshot. They don't move around in the archive. When you create a tag, version 1, it points to that snapshot. Version 2 always points to its snapshot. Okay, so that handles tagging. However, there's a related issue to tagging. We need to be able to track changes to older versions, even though that development is happening on a more current version. Let me give you an example of that. Suppose we have our archive that looks like this, and we're going to make a small addition to our archive. We're going to add something called a branch. We'll get to what a branch is here in a moment, but for right now, it's kind of like a tag in that it points to a particular snapshot. We're also going to rearrange head so that instead of pointing to a snapshot, it points to a particular branch. Now, we go in and we want to commit changes that we've made in our project directory, in our working directory. So let's go ahead and create a snapshot and we'll see this. The master branch pointer moves to the new snapshot. So every time we create a new snapshot, the branch moves. Now, tags don't move. Like I said before, tags always point to the same snapshot, but the branch pointers, they do move. So as you make new snapshots in a particular branch, that branch pointer moves and keeps track of the latest snapshot in that branch. Now the head pointer just points to the branch that we're looking at this point in time. So branches, they keep track of the latest snapshot on the branch. The head pointer keeps track of the current branch. Now, let's suppose that we found a bug in our project. And that bug happens back in version 2. Now, we've already made changes to the code base of version 2. We're getting ready for version 3 and we're working on it. And we've made several commits already. But we found a bug in version 2 and we got to go back and change that code, fix it, but yet not include the changes that we've already made in getting ready for version 3. So to do that, let's go and check out version 2. And our checkout command goes and finds the version 2 tag, finds the snapshot, points head to that, and then moves all the files in the archive associated with snapshot version 2 into our working directory. So our working directory contains exactly what existed at the point in time we created version 2. Now we go and we fix the bug, which involves editing a few files. We get the files changed. We're ready to make a new commit to our archive. But where's it going to go? We don't want to put it on the master branch because that's stuff that's getting ready for version 3. We want to put it in a separate branch. So we're going to create a new branch. We're going to call it fix. And that just creates a new branch pointer pointing to our current snapshot that we're working on. Head points now to fix. We go and we create a new snapshot. And the snapshot goes by looking at head, finding out where that is, creating the new snapshot, copying all the files into the archive just like we do for any other snapshot. But now we're on branch fix, so the fix pointer moves forward and points to the new snapshot for that branch. So now we have two branches, master and fix. Master is the changes getting ready for version 3. Fix are the changes that we just did to fix version 2. So let's go ahead and tag this. This is now version 2.1. So that tag's not going to change. It's always going to point to that snapshot. New commits on the fix branch, however, will have the fix pointer advance. But we're done with this now. We want to go back and continue working on the code base for version 3, and that's in the master branch. So we're going to go ahead and check out master. That finds the master branch, gets the snapshot associated with that, copies all the files from the snapshot into our working directory so we're up to date with whatever is in master, and our working directory matches that now. That's simple. Now, there's one thing I'd like to point out about this, and this is something I really, really like about the CSC source control system. And that's that we didn't create a branch until after we edited the files. CSC gets out of your way. It doesn't make you think about source control all the time. It's just that when you're ready to do some source control stuff, it's there ready to accommodate you. So we didn't even have to create a branch until we were ready to check stuff into our archive. That's a really nice feature. All right, we're ready to go back and work on our changes for the upcoming version 3. And all those changes are on our master branch. But before we do any more work, we want to make sure that the bug fixes that went into our version 2.1 get merged back into master. This is what our archive looks like right now. We've got version 2.1 in a fixed branch. We've got our master branch where we got ongoing changes being done, and we want to take the changes in version 2.1, the fixed branch, and merge them into our master branch. So we run a merge command, CSC merge. We're sitting in the master branch, and so we have to tell it what the other branch is that we're merging in. CSC merge fix. That'll go to the fixed branch, and it will do a comparison between those two snapshots. And if it finds things in the fixed branch that are not in the master branch, it goes and it pulls those changes over and writes them into our working directory. So note this doesn't really change our repository, our archive in any way. It just changes the working directory where we're building our system in. Now, merging sounds complicated, but it's really not that difficult. If there's a change in fix, it just gets copied over. The only time it gets a little complicated is if you have changes in the same file. And the merge will very intelligently just interweave those changes together. So if I change line 1 and you change line 23, we get a merged file with the changes in file 1 and in 23. It gets a little bit complicated if there are changes on the same line. And then our merge software can't really figure out, should it be the way it is in master or should it be the way it is in fix? In that case, it falls back on you to resolve. So it's going to inform you of any conflicts that it found in the merge process, and it's going to let you go in and edit those conflicts and make it be the right thing. So there might be some manual intervention involved in this merging, but oftentimes it just works without any fuss. Now, all these changes are put into our working area, not into the archive itself. That allows you to resolve conflicts and make any changes you want to do before we make a final commit. Once the conflicts are resolved, we're ready to do that. We create a new snapshot. Now notice the snapshot is created in the master branch, so the master branch pointer moves up to the new commit. But there's something really interesting about this latest commit, and it has two parents. It keeps track of the original master branch parent that it was on, but since it was a merge commit, a commit made after a merge was done, it keeps track of the fact that, hey, the fix branch had a part in this too. So by looking at that particular commit, we can tell that it has all the changes from the original master branch and all the changes that were from the fix branch. And so now we have a merge of the fix branch and the master branch, exactly what we like. Now you may have noticed that up to this point in time we've been assuming that the archive has been used by a single person, that the archive exists somewhere in his home directory or somewhere that he has control over. It's not a centralized repository like Subversion or something else. It's just something he's got in his own area. Now we're going to talk about sharing the archives between two co-workers. Let's assume that I'm working on this project and I've got my archive set up with all my changes in it, all my snapshots in it, a complete history of everything I've done. I've been working on this project for some time. And my boss hires a new worker, you in fact, and you want to work on the archive with me. So I set up a web server of a sort that'll serve up files out of my archive, and I give you a URL to that server, and you run a clone command. Clone, and you pass it the URL for my archive, and the CSC system will go out to the server running on my box and pull all the files in my archive over to your archive. And now you have a complete copy of everything I've done, all the commits I've made, all the snapshots I've made, and everything in it, leaving you the chance to work independently from me. Let's say you do. You go and you make some changes. You have some patches to make, you commit those to the archive, and now I need to get those changes back into my archive. So you do the same thing that I did originally. You set up a server on your box that serves up files from your archive. You give me the URL for that archive, and I do a pull command. The pull command goes to your repository, to the server serving up your repository actually, and will pull over just those files that I don't have. Now remember, the repository is additive, so you don't change anything. So what you originally copied over is still in the archive. I only need to go out and fetch those files that are added to your archive that I do not yet have. That's a fairly simple thing to write. It'd be easy to write a server that did that type of thing. So now I've got all your changes as well, and we can do that back and forth. I can make some changes and you can pull those. You can make some more changes and I can pull those back. And between the two of us, we got two archives working separately but kept in sync through pulling the new files from one to the other. So let's talk about some common uses, some common remote uses. A lot of times, if I'm working on a project and I'm not even sharing with anybody, I'll go ahead and create a CSC archive for it. That way I can keep track of the history, and if I make a blunder, I can go back in time and fix the changes and just look at that. However, that's not always enough. Sometimes I want to be able to move the archive off my laptop onto something a little more stable. In case my laptop gets lost, I won't have lost all the software that I'm working on. So I might set up a remote repository, a remote archive that has a copy of what I've got, and I can push and pull to that remote archive just like we did in our previous example. Now this again is just me working alone. I'm making changes locally. When I want to push, I just push out. And notice that creating a snapshot is something I do in my local archive. Push is something I do to a remote archive. So they're two different operations. I can make 20 commits on my local and push them all with a single push command out to the remote archive. So they're separated. Now let's say you want to work on my project with me. I can give you access to my remote archive. We'll make it a shared archive, and you can push and pull your changes up to that. Now this is really nice because now we can share changes even when we're not directly connected. You might have your laptop shut down and I want to get your changes. I don't have to worry about you keeping your laptop up and running all the time. I'll just go to the shared archive and pull the changes down from that. However, should the shared archive go down or we lose an external internet connection somehow, we can still set up the push-pull between our two local archives. That's fine. Now, truth be told, a lot of people are a little bit worried about a flexible source control system like this that can push and pull across the way in whatever combination at once. They're afraid it's going to turn out to look something like this, where people are pushing and pulling across the way, and you have no idea where the most recent copy is, and you have no idea where the master version of something is, and it's just mass confusion. Actually, most projects don't work like this. Most projects go ahead and set up some kind of master central repository, and then everybody pushes and pulls to the master repository just like you would if you had done it with Subversion. Now the advantage to this way though is that if you ever have a need to push sideways and not go through the central one, you can. Or perhaps you're working from home or on a train where you don't have network access. You can still make all the commits you want and then commit to the central repository when you get back online. It still gives you a lot of flexibility, but without tying you to be always being on the network all the time. There's other ways you can set up your project. This particular way is good where everybody is a peer. Everybody has the same rights to a central repository. Everybody can write to that central repository. A lot of open source projects aren't like that. A lot of open source projects are led by a single or a small number of developers. Here's a situation where I have a local archive for my open source project, and I have set up a master remote archive. And the master remote archive is available on the internet. It's on some server somewhere. And so it's available whether my laptop is working or not. Now someone comes along and decides they want to contribute to my open source project, so they pull down the changes into a local repository of their own. And they can make changes in their archive all they want to, and when they're ready to give the changes back to the project, they cannot go and write them directly to the master archive. The reason is that I own the master and the local archive. Well, obviously I own the local one, but the master one is writable only by me. To the entire rest of the world, it is read-only. So they can't push back to the master repository. What can they do instead? Well, the simplest answer is to go and create their own remote archive that's up on a server somewhere. You can imagine that there might be some kind of market for something like CSC Hub, where people can just create remote archives quite easily. They push their changes up to their remote archive, which they have write access to. They then send me an email or some kind of notification that says, hey, I've made these changes to your project, and they're here in this archive. Here's the URL, and here's the branch that you should grab and look at. So I go to that archive, I pull down their changes, and I will probably put them in a local branch on my local archive. And the reason I do that is that I can look at their changes and maybe run some test cases or examine the source code, and I can decide whether I like their changes or not. If I don't like the changes, I can toss the local branch and just get rid of it and ignore it. If I do like the changes, I'll merge that branch back into my master branch, and then I will push those changes back up to the master archive that I own. Once that's back up there, then everybody else can go and grab the changes and pull them back. And so this whole figure 8 push and pull cycle is very, very common in a lot of open source projects. Here's another way to organize a project. This way is useful for really large open source projects with hundreds of developers, hundreds of contributors. The problem with that many contributors is that the person or persons in charge of the master project archive would get inundated with pull requests. Here's this change, here's that change, and they would become a bottleneck to all the changes going into the project. So what you can do is have the project owner have a single archive and then set up lieutenants that own their own archives. And below the lieutenants, you have all the individual contributors. And things filter up this way. Suppose an individual contributor wants to make a contribution to the project. Well, he pulls down the master archive project. He makes his changes. And then he finds the lieutenant who's in charge of that particular part of the project. For example, you might have a lieutenant in charge of the file system, or one in charge of the GUI interface, or one in charge of, whatever. So he finds the lieutenant who's responsible for that piece of the system, and then he informs the lieutenant, hey, I have a change, would you look at it? The lieutenant will pull his change, he will examine it, check it for quality control, make sure it matches the goals of the project, and the lieutenant might then pull up some other changes, and when he's got a fair number of changes, he will inform the project owner that, hey, here's a new update to the file system portion of the project. The project owner pulls then the changes in one big chunk, and he trusts his lieutenant to do a lot of quality control for him. That way, a single person doesn't become a bottleneck for all the changes, and this scales very nicely to large projects. In fact, the Linux kernel is designed this way with several levels of archives and lieutenants. Wow, what a journey we've had. Let's wrap up things right now and do a little summary. We started off with some really basic requirements for a source control system, and we developed it ourselves. And each step in the way was a very simple step and made sense at the time. And we ended up with a really flexible source control system that does exactly what we want. It contains a complete revision history of everything we've done. It's very efficient in storage. We have guaranteed integrity of the archive. We have ways of sharing the archive amongst multiple people. It's very easy to do. We have cheap branching, and we have easy tagging. Now, I will confess, of all of these, the thing that I like the best out of the system is the cheap branching. The fact that I can make a branch, do a little bit of experimentation with it, even make some commits, and then decide to merge it back in or not merge it back in, gives me a lot of flexibility in the way I do software now. It's incredible the way it's changed the approach that I have to this. Now, if you're listening very carefully, you might think that our CSC software actually sounds a lot like Git, and you would be right. What we have done is we've described the Git source control system kind of from a bottom up. However, we left out a few details. Snapshots, that's what Git calls commits. Project archives, those are repository. In fact, you probably heard me say repository several times. The reason I call them archives in the presentation is that the first time I gave this talk, people heard the word repository and thought of something huge and humongous, and the fact you would have this repository sitting on your local disk scared them, actually. If we think of it as a simple project archive where we save changes, that's a much kinder concept, and they were much more accepting of that. But it's a Git repository is all it is, very lightweight. And what we call manifests, those are trees or directories in Git terminology. The commands we introduced are very similar to the get commands. And you can see there, the snapshot is really a commit in Git. Everything else is more or less the same. However, there are some differences between our kind of simplified CSC system and what Git really does. For example, in CSC, we only have working directories where we have our source code and the repository where we store the snapshots. Git uses actually three areas. It has the working directory and the repository, but it also has a staging area that sits between it. And the reason for this is that Git is very content-based, that when you commit something to Git, you're not committing a file, but you're committing the current state of that file. So you can stage things into that area and then commit from the staging area into your repository. It goes along the lines of the whole get out of your way until I need to use source control philosophy. You can make a bunch of changes in your working directory and say, okay, now I want to commit, but I should make multiple commits out of this. And the staging area allows you to move things into that, stage it, and then move some more. And it turns out to be rather handy. I will confess it's probably one of the most confusing things to beginners in Git, but it's still quite useful. Another difference between CSC and Git is that CSC has one level of object file storage. We stored all our files in a single repository directory. And that's okay until you get up to several hundred to 1,000 files. The performance of that kind of file organization gets really slow. So Git does a smart thing. It actually has a two-level directory structure for its repository. And by having two levels there, you only have 256 directories in the first level, and then the number of directories under that, under each individual directory is much smaller, much more kinder on the file system than what we did for a large number of files. Another difference is that CSC just stores plain files. Git does a little pre-processing of the files. It will encode and compress the files and store them very efficiently within the archive itself. So that's another nice thing about Git. CSC just has some really basic features. Git has a lot of really nice advanced stuff. There's commands to manipulate the branches in interesting ways. The bisect command I would like to point out. Bisect will do a binary search through your repository to find when a bug was introduced. And I've used it on several occasions that have saved a lot of time in tracking down where bugs happened and what commit they happened on. Really useful stuff in Git, and I highly recommend it. Finally, we have some references for those of you who want to research the internals of Git a little bit more. The Git from the Bottom Up PDF by John Weigley is very good, and I recommend that, along with the Git Internals PDF by Scott Chacon. Scott is one of the guys who works on GitHub, and if you have a chance to hear a presentation by Scott on the topic of Git, go and take advantage of that. Scott is a wonderful presenter and gives lots of information. In fact, he gives about 2 hours of information in a half-hour talk, so you got to listen really carefully. But go and hear him if you have a chance. Hey, thanks for listening. I really enjoyed sharing this talk with you. I have found that understanding a little bit of what goes on under the covers of Git makes me a lot more comfortable with using the Git commands and being able to do a lot more with Git and to be able to do it with confidence. It removes a lot of the magic feel from Git. I hope that's the same with you and that you now are encouraged to go give Git a try and maybe use it in a new and exciting way. Thanks so much. Have a good day.